Welcome to the debate. Today, we're digging into, well, a really quite provocative idea in theoretical physics that's emerged recently, the time force hypothesis, or TFH for short. It's an attempt to unify basically all of physics, quantum fields, gravity, the works, by starting from a single universal principle.
And that principle, if I understand it right, is that irreversibility, the arrow of time, isn't something that just emerges from complexity, but it's actually fundamental. The TFH posits that all the dynamics we see stem from just one equation, a sort of damped, nonlinear wave equation for a universal scalar field.
Exactly. The central and pretty radical idea is to bake physical friction or damping right into the foundations of reality. This is governed by a universal constant, let's call it alpha zero, which acts almost like the universe's underlying rhythm or pulse. And here's the kicker. TFH identifies this constant alpha zero numerically with the current rate of cosmic expansion, the Hubble rate, h0. The value is tiny, something like 2.29 times 10 to the negative 18 inverse seconds. But the claim is this single minuscule friction rate dictates, well, pretty much everything from why time flows forward to how fast the universe expands.
Okay, so the core question we really need to wrestle with today is this. Does the time force hypothesis, by making this intrinsic irreversibility a primary axiom, actually give us a necessary and, importantly, consistent way towards unifying physics, maybe solving some deep puzzles? Or, and this is my concern, do its fundamental violations of time reversal symmetry and, crucially, conservation laws just create insurmountable conflicts with the, frankly, stunning precision of theories we already trust, like general relativity and quantum field theory?
Well, I'm going to argue for the first case. I think TFH offers a remarkably minimal, consistent unification. It forces us, yes, to flip our usual way of thinking, but maybe shows that true unification requires this kind of foundational irreversibility.
In my perspective, starts from the cost of that flip. While the ambition is definitely admirable, I believe TFH's inherent non-conservative nature creates a fundamental clash with established, high-precision physics. It sort of backs us into a corner where we have to accept modifications to our most successful theories, modifications that are right now largely unconstrained by experiment.
Okay, let's lay out the case for unification then. Let's focus on what this radical inversion actually buys us. By starting with a damped master equation, you immediately get a handle on the mystery of the second law of thermodynamics. See, irreversibility isn't just a statistical effect of large numbers anymore. It's a dynamic necessity built right into the universe's, you could say, source code. And this is mathematically solid. There's this thing called a Lyapunov functional, basically a total energy function for the system, and it's mathematically guaranteed to decrease monotonically over time. So dl over dt is less than or equal to 0. That gives you a first principles derivation of entropy production. Everything fundamentally has to run down.
I can see why you'd emphasize the mathematical elegance of deriving the second law that way. It is neat, but you have to admit, that neatness comes at the cost of ditching a core assumption of classical mechanics, that the fundamental laws are time reversible and that energy is exactly conserved locally.
But look at what abandoning that assumption potentially buys us. Massive unification. By setting the microscopic damping rate alpha zero equal to the macroscopic expansion rate h0, we automatically generate the universe's large-scale acceleration. It tackles the cosmological constant problem not by just adding some mysterious vacuum energy, but by suggesting that effective dark energy is simply the consequence, the cost, if you will, of this universal damping itself. And importantly, we recover standard physics in a controlled way. If you mathematically turn off the damping, let alpha zero go to 0, then QFT unitarity, time reversal symmetry, and those conserved know-their currents, they all pop back out exactly.
Right, but that relies on the vanishing limit, the idea that it's almost 0 but not quite. That's precisely where the fundamental conflict emerges when alpha 0 is actually greater than 0, however small. Let's focus on general relativity for a second. GR is built on this beautiful geometric idea that energy and momentum are locally conserved. The divergence of the stress-energy tensor is 0. But in TFH, that stress-energy tensor gets modified, meaning energy and momentum are not locally conserved. They leak, fundamentally.
Okay, but the non-conservation term, the one that scales with alpha zero, it's incredibly tiny in, say, the near vacuum of space.
It might be tiny in a simple vacuum, yes, but the theory itself introduces this environmental factor, a susceptibility called chi. The effect of damping alpha ES isn't just alpha zero, it's chi times alpha zero. And this chi factor, it depends on the local conditions, density, vorticity, stress. Near really massive objects or say black hole horizons, the calculations within the theory suggest this factor chi can just balloon to enormous values, maybe 10 to the 18 or even higher in some scenarios. So in those dense high-stress regions, that non-conservation term suddenly becomes potentially very significant.
I see why that sounds alarming, but the framework addresses this by essentially being careful about the system boundaries. The total system, if you define it correctly, including the scalar field bath, is argued to still be conservative. The non-conservation you're pointing to is local. The idea is you compensate for it by defining an effective stress-energy tensor that includes this sort of leak accounting, the energy being dissipated into the universal scalar field bath.
That sounds a bit like a mathematical maneuver to preserve a definition, doesn't it? If local energy conservation is the absolute bedrock of general relativity as we understand it, how can TFH possibly square with the incredible precision of the solar system tests we already have? I mean, planetary orbits are governed by locally conserved gravitational fields. Introducing local energy leaks, even if they're tiny most of the time, seems like it would threaten constraints on things like the post-Newtonian parameters, which we've measured with frankly astonishing accuracy.
But the modifications are kind of designed to be most relevant precisely where standard physics already seems to break down, which is exactly why they're so hard to pin down in the solar system. For standard, low-velocity, non-extreme gravity situations, chi is expected to be very close to 1, and the effect is indeed minuscule, likely below current detection thresholds. Where TFH potentially really makes a difference is in providing a mechanism for phenomena we currently attribute to things like dark matter. The theory actually predicts an environment-dependent dark matter phenomenology. It's sourced not by some new exotic particle, but by this rotational susceptibility chi-r.
Meaning what, exactly, in practice?
It means that the extra gravitational pull needed to explain galaxy rotation curves, what we usually call phantom mass, is actually sourced by the shear and vorticity within the galactic disk itself, mediated through this damping function. So you get modified galaxy dynamics where the total acceleration isn't just baryonic gravity, it's baryonic gravity plus an additional term related to this damping acceleration. Now, this is highly specific and crucially directly falsifiable. You could in principle test this by correlating the observed shear in a galaxy with the inferred distribution of this phantom mass. That's a test that standard particle dark matter models just don't offer. It's about economy of mechanism, dark energy and dark matter effects potentially arising from the same underlying physical principle.
Okay, I appreciate the attempt to sort of quarantine the non-conservation effects to cosmology and extreme gravity. But the problem doesn't just stop with gravity, does it? If conservation laws are fundamentally only approximate, this must bleed into our quantum theories as well. So let's pivot to THC's impact on the quantum scale, specifically this issue of non-unitarity.
Yes, definitely a crucial area to discuss.
Quantum field theory, QFT, is built on the principle of unitarity. Basically, the requirement that the probabilities of all possible outcomes in any interaction have to sum up to exactly 1. TFH, by introducing this fundamental damping, alpha F being greater than 0, makes the theory intrinsically non-unitary. Mathematically, what happens is it shifts the poles in the spectral function off the real axis. What that means in physical terms is that all particles fundamentally acquire an intrinsic built-in decay width. They're not perfectly stable.
Okay, but pause for a moment and think about the scale of that width. In a vacuum, the calculated vacuum width floor is minuscule. We're talking something like 7.5 times 10 to the negative 34 electron volts. It's almost unimaginably small. It really shows how profoundly close TFH can be to standard QFT in quiet conditions, like a vacuum.
The real question isn't whether it technically violates QFT unitarity, but whether we could ever hope to measure a deviation that tiny in most situations.
But again, the problem potentially blows up when high gets large. We need to be able to rigorously prove that this inherent non-unitarity stays hidden beneath our current experimental limits, even in high-energy environments like, say, heavy ion collisions, or in ultra-precise measurements of particle decays. This forces the TFH framework to essentially abandon the standard mathematical guarantees of QFT consistency, things like the ward identities, which are the mathematical expression of symmetries leading to conservation laws.
Well, we don't quite abandon them. The idea is that they become softened.
Exactly. Softened. Which means we have to rely on some rather complex mathematical approximations, these soft ward identities, to argue that conservation almost holds perfectly. The burden of proof here is immense. It rests on showing that this inherent decay, this intrinsic non-unitarity, has somehow been completely missed by decades of increasingly precise experiments in QED and the strong interactions. That seems like a monumental task.
I understand why you frame non-unitarity as a weakness, but I'd argue, perhaps counterintuitively, that this regulated decoherence is actually a feature, not a bug. It offers a potential foundational solution to the measurement problem in quantum mechanics. Instead of needing to invoke somewhat ad hoc ideas about wave function collapse, TFH provides an objective decoherence mechanism. It predicts a specific Lindblad-type evolution with a rate proportional to alpha f. In a sense, the universe itself objectively causes quantum states to decohere through its own fundamental damping.
But that just shifts the problem, doesn't it? It shifts it from where does collapse happen to how can we be absolutely sure the amount of collapse predicted by TFH hasn't already been ruled out by existing precision experiments that rely on quantum coherence.
And that brings us right back to falsifiability. This damping isn't just arbitrary noise. It's proposed to generate specific, testable structures and effects. For example, in the realm of strong gravity, TFH predicts there should be observable extra damping in gravitational wave ringdowns, the final vibrational settling of a merged black hole. This extra damping, which should scale with alpha f, is something that LIGO, Virgo, and future detectors could potentially constrain, putting specific bounds on how large Ki can be near black hole horizons.
And that, of course, relies on the mathematical derivations connecting the fundamental TFH equation to these ring-down predictions being perfectly accurate and generalizable across different astrophysical scenarios. It's a tall order.
It is, no doubt, but consider the potential theoretical payoff on the quantum side as well. The TFH framework, while speculative here, offers a potential path towards solving the Yang-Mills mass gap problem, one of the Clay Millennium Prize problems, a huge unsolved issue in fundamental physics. The theory suggests that the stability of vortex-like structures, which are related to confined particles like glue balls in QCD, is limited by the damping rate. This actually leads to a theoretical prediction for the Yang-Mills mass gap of around 1.63 giga-electron volts. Now, that value is intriguingly consistent with results from large-scale lattice QCD simulations. The very fact that the same damping constant that might regulate the cosmos could also potentially determine the mass of the lightest glue ball. Well, that feels like a profound hint of unification, doesn't it?
That is undeniably an exciting predictive claim, I grant you that. But it brings me to my final major concern, which circles back to the empirical fragility of the whole setup. The entire, quite ambitious structure of TFH rests fundamentally on one single empirical observation, the current measured value of the Hubble constant, h0.
I'd argue that the decision to identify alpha 0 directly with h0 is its greatest strength. It drastically reduces the number of free parameters, making the theory highly predictive.
But h0 is notoriously tricky to measure. There's ongoing tension between different measurement techniques, and the current uncertainty is around, 2.2%? Because every single derived scale in TFH, the characteristic length scale, L alpha, the time scale tau alpha, the effective critical density rho c, is fixed by this single constant. They all inherit, and in some cases might even amplify, that uncertainty.
If future, more precise measurements shift the accepted value of h0, then the entire quantitative structure of TFH has to shift with it. That includes potentially sensitive predictions like particle mass ratios derived from these field profile integrals. It feels like the theory's foundation is constantly dancing to the tune of ongoing cosmological measurement uncertainties, which makes it seem empirically, well, fragile.
Alpha 0 equals H0 maximizes predictive power and ensures the theory is maximally falsifiable. Instead of seeing the uncertainty as fragility, see it as a tight constraint. The theory doesn't just make one prediction. It generates a whole checklist of observable signatures, which should all scale with the same fundamental rates, alpha f, but across 4 completely different domains of physics.
You mean things like the gravitational wave damping we mentioned, the cosmological redshift drift, potentially some lab-based coherence length measurements, and these particle mass ratios derived from the theory?
Precisely. If we detect extra damping in gravitational waves that scales exactly as predicted by this universal rate, and we measure a cosmological redshift drift over time that aligns with the same rate, and that rate helps explain the Young-Mills mass gap, then these redundant cross-domain predictions provide incredibly strong confirmation. Conversely, if TFH fails decisively in just one of those arenas, the whole structure's in trouble. That, to me, is the hallmark of a powerful scientific theory. It sticks its neck out and is uniquely vulnerable to being proven wrong.
We certainly agree on that. The hypothesis definitely presents clear points where experiment could, in principle, falsify it.
Look, the real strength of TFH, I think, lies in its bold inversion of causality, making irreversibility the fundamental source code. It attempts to unify gravity, QFT, and thermodynamics under one measurable, universal rhythm. Everything flows, everything damps. It offers a pathway, however challenging, toward a genuinely testable grand unification.
And while it is minimal in its starting point, TFH forces us to accept that cherished conservation laws are at best approximations, dependent on this rather complex energy accounting, this leak accounting mechanism. Its ultimate success, I believe, hinges entirely on whether this intrinsic non-unitarity, encoded in that environmentally dependent susceptibility factor, key, can be rigorously shown to consistently hide just beneath our current experimental limits across all energy scales, from that incredibly tiny 10 to the negative 33 eV vacuum floor, all the way up to the potentially high susceptibility domains near black holes. The experimental and theoretical gauntlet it has to run remains immense.
And alternative picture of reality. And for that reason alone, I think it warrants a really rigorous, experimental, and theoretical audit, regardless of whether one ultimately buys into its core principles or not.